before this, if I ask you, I think we've done sorting, right? So let me ask you a question now. You see the Singapore data before the probability distributions. Now, let's assume okay, so let me just sample. It's 7843, right? I'm going to call someone to tell me what this will give me. My friend, are you seated now? Yes. What's your name? Oh, you can say that. What's the name? Derek. Okay. Derek, what is the function of this code? What should we expect if we run this? Yes. Okay, so first of all, this one, what should we expect? What? We are going to... Please keep quiet so that I can hear you. Yes? One to 7. Okay, good. Okay. Next person. Okay, so you understand what you said. We'll get a sample of 20 observations. Now, if we pass that one through this, what are we going to get? Yes. Hurry up. Hey. Yes. What element? 20 elements. What? Describe it properly. So one of the elements will be what? What do you mean by the element? Yes. What's your name? Stephen, what do you mean by the element? Next person, yes. Is that how you talk? Or you want to come here and tell us? You have sore throat. I also have some, but I'm talking. Yes. What did you say? I said, what are we going to get if we run this code? So you are not here with us. Next person on your left. Yes. What are we going to get if we run this? Don't look anywhere, you are the same person. Yes. What is the element? Is it the one in an ion? The element, is it the one in ion? So tell me, what is it? Variables. Which variables? So one of the elements will be what? The element you are talking about. What will it be? If you take, let's say, the first number, what element would that one be? The what? You finished running it. My friends. Yes, you tell us if you have finished running it so that we can move on. What is an element? The element they've been talking about. They are randomly sampling. That one they've said it. But one of the elements they are talking about is what? You are now going to check what you read. Who can help us? Yes. Yes.
Yeah, so they are sampling some rows from the data frame.
Yeah, so what I want you to tell me are rows. And the rows are what? They are. What are the rows? Please, what are the rows? Up to now, you haven't finished copying this and running. What are the rows in this data set? Okay, so if you run this, you are going to get something like this. So each row is what? Each row is what? Just an observation. In this case, these are claims data. So if you pick one row, that is one person. So for example, in my case, the first randomly selected person is 4225. The person is a male. Sex of the insured male, so of course female 0. Vehicle type is APC is 1, claim amount is 0, ESP weights, and so forth. So it will run through all the 15 variables. Okay. Please, is everybody okay with this? So my next question. So we are still going by that rule. Next person. So if let's say I name this as claims. The one sitting beside you. What's your name? Pardon me? Collins. Okay. Collins, what will this one do now if I run this? What will be the result of this? I think maybe I should be asking you like you do in Mass 220. That one you interpret the codes on the paper, isn't it? Is that what you want? Oh, that would be easy, like this one. Yes, what are we going to get if we, or how do you understand this line? To that one. Okay, good, okay. Please, everybody should listen. Now, what I want to do is that, you see, there are 15 observations here. Claims and so forth. So let's say I want to arrange these values such that we move from the highest ESP weight to the lowest one. We do this in Excel, right? In Excel, if you go to data and you do filter, or you highlight all of them, but it's easier if you use filter. Then you either largest to smallest or smallest to... We can do so over here. Okay, so that's what I want to ask you. Okay. Now, if we are to arrange it such that the one with the highest weight will be on the first row and the minimum weight should be on the last row, what should we do? We should, so that's your assignment. Okay, or somebody wants to answer it. You want to?
So who will be sorting the weights?
We will sort the weight.
So then we can use sort.
Sort. But, okay, so, okay. Let me take this one to 5. So that it will be very small for everybody to see. Okay, so, and then, ooh, please can you see those at the back? You can see. Okay. I want to say if I can get all of it on the same line, it makes it easier. So let's see claims. Oh, so we have some second line. Or, to make it easier, I hope people are following. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10. So let me just select only 10 variables so that we see all of them on the same. Okay, now let's go to what? What's the name again now? I can't hear you. Okay, let's continue. Okay, now you said we should sort. Okay, what you need to... Okay, so in Excel, you can... I think when you highlight, you can sort without expanding, right? And the other will tell you, as I think some of you do not even do this. As for Excel, you will have to make sure that you know how to do it. We won't have that time to teach you here. Okay, but it will be bizarre if you go to an organization, you can use how to do an Excel, they give you Excel, you can't. Not many people will know how to use that. By Excel, they will. So please make sure you know Excel. At least you can use YouTube to learn. Okay, that you can sort, you can do VLOOKUP, you know, join cells using one column, and it's very important. Other than you waste all your time picking from here and then you make mistakes and so forth. Okay. Now we want to be able to sort. It means if I sort weight, I cannot do so by sorting only the weight. If I do that, what will happen? Somebody's weight will be assigned to another person. Is everybody okay with this? If I sort only the weight, it means, oh, it's been sorted already. So what we want to do has already been done. Do you get what I'm saying? Because the highest weight is what? 0.91. Okay, so we will rather do it the other way around, right? Good, okay. What should we do now? You said we should sort. Which one?
So, since we want to sort the weights, we have to first call out the weights.
We'll call out the weights from the data. How?
So, S.claims weights.
Dollar weight. It's this one, right? Okay, yes.
Then to assign it to we get assigned.
I should do assignment. Oh, it's not? Okay. Like this. Okay. And then
If the S claims,
I should repeat it.
but then if the sort function,
I should bring salt like this. The weight. Okay. Yes. Decreasing to true. Okay. That's all. And I'm done. But that's all what you get. Okay, so this one, what is it going to give us? Just the sorted data. Okay, so, okay, whatever you say, there's something wrong. Where? Ah, okay, it's the N's. What happened with this? Okay, let me do this. I think it selected a row that had N's. One, two, three. Is it 473? Let me just take one. Yes. I have to. Okay, so this it won't work. This will only sort the claims alone. What I want you to do is to reverse the selection. So what do we do? Okay, so I will leave it to you as an assignment. And then we move on. Please, is everybody okay with what you have to do? So if you are able to do this, then you can do the entire data, right? What I want you to do, yes.
So what about the function order?
Okay. So it means we talked about this. So I want you to revise. That's what I'm saying. Okay, so you need to order. Have you found it now? Pastor? Okay. You can order, or, I mean, there are so many ways to do this. And then you can also sort by use the IDs. So if you sort, it will now, I mean, if you choose only the IDs as well, then you pass it through it like this, right? And then it will rearrange them in the same format. Okay, take it. There's a video on this that on the YouTube page. So just go through it. I think it's just about 15 minutes. Sorting, ordering, and ranking. Because we've already used ranking, which is for the Spearman's rank correlation when we're doing it. And we've done sorting as well. Of course, it will take the values and sort it, either decreasing or what? Increasing order. What is left is ordering. So when you order, it will rather order the position, right? And so forth. Okay, so that's it with that. Let me move on to what I want to talk about. Any question? So this, you can't use sort. Sort will just sort the actual values. Yeah, but that's not what you want. You want to be able to rearrange them. Then you can use the whole data, yeah. So that if you do it, it's like if you take, but you can't display the whole data. That's why I was taking just part of it. It's 7,008. But if you do it, you can take a sample to show that it's actually decreasing or what? Increasing. So, okay, so let's move on. Now, probability distribution. Soon we will be moving to your star 333 to talk about estimation. So before we do that, we need to know how are um, uh, how should I put it? How distributions are stored in R, right? So if we take normal distribution, okay, remember that in distributions we have density, we have the cumulative distribution, we have the quantiles, and also we can generate observations from a distribution. So in R, you have R to represent random variate. In other words, just like when you say X is from a normal distribution with mean, that so that X is your random variate. So if I want to generate observations from a distribution, I'll use R. Maybe if it is normal, R norm, right? And then we get those distributions and so forth. So let's look at this. So I talk about normal distribution. So R norm like this. So it says this is all normal, and it is in what package? Stats. Okay. Now, so if you look over here, see the normal distribution, density distribution, the distribution function is the cumulative distribution. Then we have the quantile function. You know about quantile functions. What is a quantile function? You remember your order statistics in 331, haven't you done it? You did. Where's my dear? Okay. Or you find the inverse of a function. Can you please write the CDF of exponential random variable? So X is exponentially distributed with parameter lambda. Write down the PDF, the CDF, the survival function, and which one again? Then the quantile function. So X is exponentially distributed with parameter lambda. So write the density function f small f of x. Then you write the CDF. The CDF is what we call in R, it's called distribution function, or the cumulative distribution function. Then when he comes, I'll explain what the quantile function is. But are you done? So write the survival function as well. What's the relationship between the CDF and the survival function? Good. So you that will be easy. Are you done? We are going to write functions in R to do all this. So please make sure you've written it down. Let's see. Okay, all right. Okay. So you have to, what is the range of the X? Or the domain, I should say. Okay, positive, yeah. Please, are you okay? Okay, now I want you to find the inverse of the cumulative distribution function. Find the inverse of the cumulative distribution function. That is the quantile function. So please find it. Which means you have to equate f of x to equal to, let's say, p. Remember, f is also a probability, right? You remember your cumulative distribution. So we say that x is exponential lambda. So our f of x will be equal to 1 minus e to the power negative lambda x. Of course, x greater than 0. Is everybody okay with it? Good, okay. So the inverse of this function is what I want you to find. And it is what? It is? It's the quantile function, okay. So it means that I can write this as P. Why do I write this as P? Because this will be like it's from the uniform, right? You remember the F is between 0 and 1 as well. So it's a probability. This is 112, right? We talked about this. I thought some of you here, we talked about this. Good. Okay, so if we find the inverse over here, that means S with some small p will be equal to what? You are waiting for me. Okay, so 1 over lambda log 1 minus p. Okay, yes. Whichever one you use. Okay. Now I can write this as scale p. This p is that small probability you have it over here, right? Okay. Of course, I could have also said just x. Okay, but if you write x, it goes with some p. Because if I get a p which is from a uniform distribution, I can get this. And this is what we refer to as inverse probability transfer. What does this mean? It's a crucial principle in statistics that I can generate observation from any distribution by linking it to the uniform distribution. Uniform distribution is easy. We all know f of s is 1 over b minus a, right? And so forth. If a is less or equal to b. Now, what this means is that if I want x, remember that these x are from where? Exponential, right? Is that okay? Okay. What I can do is that if I want x from, let's say, a uniform distribution with lambda 0.5, then what I need to do is that I can use this log 1 minus p. Then I will generate this p from a uniform 0, 1. Anything that I do here, these x's are now of this distribution. Please, is everybody okay with this? Not okay. So you need to follow. My dear friend, are you here? Are you with us? What did I say? You are not here. Oh. Okay. So let's listen. Okay. What I'm saying is that if we have a distribution, any distribution, whether normal, chi-square, t, and so forth, if we have the distribution function, then we can generate observations from it. Is that okay? Now, it is not every distribution that you can find in R. Okay? But, if I know the distribution function, then I can easily generate observation from it by linking it to what? The uniform distribution. Why do I say so? Once I know this, I know that this is a probability, right? Okay. So what I will do is that I will find the inverse of this because the x are the random observations. Okay. So if I find the inverse, then this f is a uniform distribution because it's a probability is a number between 0 and 1. So that's a standard uniform distribution, 0 and 1. So we simulate and then we can now get the observations from here. Please, is everybody okay with it? As for the inverse, that's also another problem. And that's why you do mathematics, right? Okay. So, if I can't find the inverse, what else can I do from your knowledge in mathematics? The inverse may not exist, or it's intractable. I can't find it. Or I should give you maybe the normal distribution. You find the inverse for me now. You see, it won't be easy, isn't it? Yeah, so it's not every distribution you can easily find the inverse to use what we are using now. But you've done a bit of numerical methods, right? Okay. What were you doing in the math 220? Okay. So we. Okay. Please listen. Which one? Okay. So if we cannot find the exponential, is easy. So as soon as you can find the pi is easy. What is happening is simply this: that if I have a distribution and I write it as f of x is equal to p, remember, as I said, f is a distribution function, but it's also a probability, right? So this probability is a number between what? 0 and 1. Is everybody okay with it? Okay. So if the inverse exists, then if I apply this inverse, what will happen? I have that. Okay, f inverse throughout, right? So f of f inverse, I get x, right? So this is what we will refer to as the quantile for the probability p. Is everybody okay with it? That's what we did with the exponential. Okay. Now, what if this inverse, if the inverse does not exist or you can't find it? What do you do? That's why you study mathematics, as I was saying. I will treat this as an equation, right? And find the root. In other words, I can rewrite this as what? F of x minus p is equal to 0, right? Okay. And this you can solve from your knowledge in calculus. And numerical method. I'll show you an example soon. So those in my master's class, that's what we do. So that it's a bit different from what you do at the undergraduate. But I'll show you an example. Okay. Other than that, we can't, if we have distributions, we cannot simulate from it. And you see, let's say if you are studying claims data, they may not follow the distributions you know, the everyday distributions we know. Is that okay? Sometimes you get new, or you study the data and then you come up with a new distribution. Such distribution will not be in R. Okay, so if you are able to solve it this way, like the first one, then that's easy. We're able to solve it, so we just simulate observation from a uniform, pass it through it, and then we get our samples. Okay, but if we are unable to, so let me. Let me show you an example. Okay. So let's look at this. So okay. So this is a paper we published in Journal of Applied Statistics. Okay, so it's about loss distributions, right? On some claims data. Now, so I'll show you that this is the chain distribution. Okay, so you see this distribution has only beta 2 as a parameter, right? Okay. So we can also do some transformations to get more parameters to. So the first one maybe is just shape, but we can introduce location, we can introduce another shape parameter, another scale parameter, and so forth, so that it caters for several situations, right? Whether it is left skewed or right skewed, whether it is bimodal, and so forth, okay? Because when you have data, they may follow different patterns, okay? So if you have a distribution that will be able to cater for all of them at a go, depending on the structure of the data, then that's better, okay? Now, so you end up deriving the PDF or the density function as this. So the question is, will you be able to now find the CDF and invert it? Okay, so that's the sort of thing I'm talking about. Okay, so if you look at this, so that's a CDF, that's a PDF. Okay, so in this case, they have only two parameters, beta 1, beta 2. But this is a transformation of the first distribution I showed to you. Now, the beauty of this is that you see over here, it caters for several shapes of the data. So if you have a data that is right skewed, some will be bimodal, and so forth, multimodal, and so forth. Okay, so in this case, we are looking at something like that, right? So if I can't solve it explicitly to get x is equal to something, then I need to treat it as that. In other words, I send the p to the other side, and then I solve it numerically to generate my observations. Okay, we are not going to do that. Just want to tell you that this is really what happens. But the basic one is what we have done over here. So what we are going to do now is that we are going to get observation from exponential. We can generate one from exponential distribution, but we will also write a function like this to also generate observations from what? Exponential, using what? The quantile function of the exponential distribution. Please, is everybody okay with what I've shown you? Okay, so this one is the first case where you can easily find the inverse. But something like this is the second case where we cannot find the inverse, but we need to what? Solve the inverse or numerically. And so forth. We won't go through that one. If you happen to apply for a master's program and you come, and I'm still around, or somebody else is there, will do that. But they do it. If you want to come and listen to it, you can join them Friday. Okay. So let's move on. So now, this is what I want you to do. We've seen the normal distribution. As I said, D will be what? Density. P will be the distribution function. Remember, you wrote distribution function and then the survivor function. Is that okay? All right. So this P can represent the survivor or the distribution. So the key thing there is this argument lower the tail. So let's say we have this function as a let's assume I have this. So this is a lower tail. This is what? Upper tail, right? So if lower tail is true, it means I'm reading from this part, right? So let's say if I'm reading here and I say lower the tail is true, then it means I'm reading the area over here. You remember your normal tables and all those things. Okay. If lower the tail is false, then that means I'm reading the area over here. That is what? A survival function. Is that okay? Yeah, so if we read from negative infinity to a point, that's f of x. That is the probability that x is less or equal to what? X. Is that okay? Then our x of x would then be probability that x is greater than small x. And so forth. So that area is to the right, and then, so lower the tail false means you are reading that. Lower the tail is equal to true means you are reading the other side. Any question? All right. Next is the quantile function. If you remember, all the quantile function I've written over there is with respect to what? P. Right? Okay. So if I want K norm, I need to provide P, which is a probability. So let's look at what we've been reading in start 223 and start 333. Let's say you do a hypothesis test and you want Z, this one that you've been reading, Z 0.025 or Z 0.975. You remember this? This gives you what? 1.96, right? Okay. What about this one? It will be the negative of the other one. Is that okay? Okay. How do we read that in R? Well, we have to provide the same information. So let's copy K norm. Let's all copy it and paste it here. For log, we can take it off. It's not needed. Okay. Now P. So let's first start with 0.025. So this is when you are doing a hypothesis test, or we say find a confidence interval, and your alpha is what? 5%. So two-sided confidence interval, your alpha is 5%. This is what you do. So essentially, when you take your normal distribution, so those that I taught 223, I usually use this to demonstrate. Right? So over here will be Z, negative Z 0.025. Over here will be what? Z 0.975. Is that okay? We were reading this to get what? 1.96. Over here, negative 1.196. Why is this so? Because 0 is over here. So on the left, it should be negative. Okay. So let's do that. 0.025. Mean is 0 because we are reading from the standard normal, right? Okay. But here we can read from any mean. Remember in 112 we said that we can actually, X is normally distributed with parameters. Let's say X represents the average expenditure of students in this class. So on average, maybe in a week you spend 800 cities. So we collected data from here, we found the average, we got 800, the standard deviation was, let's say, 20, right? So we can say that X, which is our expenditure, average expenditure is what? It has a mean of what? 800, standard deviation of what? 20. Okay, we can find a probability that you find a student who will spend more than 900 cities, right? You can then standardize this and then go and read it from tables. But in R, we can easily read it straight away. That's what I want to put across. Okay, so let's do this. So the standard deviation is 1, that's fine. So if lower the tail is equal to true, then it means we are reading the quanta on the left-hand side. Is that okay? So let's run it. And that's what we've been seeing on your normal table. Is everybody okay with this? Okay. Now I'm going to set this to false. If I set it to false, it means we'll read all the other side. All right. Then that will also be the same as reading. So you have to, false. Okay. Now remember, I can also get this same thing by using what? 0.975. Which means it's going to change the other way. If this is lower dot A is false, it must be true, and the other like that, and so forth. Is everybody okay with this? Yeah. So you can use this, but if you are using it, you have to be careful to know that if your lower tail is true, then 0.05 you are reading on the left-hand side. If it is false, you are reading on the right-hand side. Yes?
So is it that for the meaning and standard deviation, can you also vary them? Like,
You can vary, but if it's standard normal, then it must be 0 and 1. Yeah. That's what I was saying. Yeah, he wasn't. Okay. Is everybody okay with this? So this is how we find quantiles. And all the tests you've been doing, chi-square, f, all of them we can find it. T, and so forth. So for quantiles, we use scale. So let's say if it is T, then we need some degrees of freedom, right? And so forth. So I can start by QT. So for the T distribution is QT. So let's do this. So this is what? Student T distribution. Okay, so during star 223, if we say that you don't know your mean and so forth, we can find this point, let's say 0.25. If our degrees of freedom is 4, you were reading this from the normal table. Lower the tail is true, then we expect to get what? Negative, right? Something like that. There. Is everybody okay? Now, if I change this to false, I get the opposite back. We can do so for chi-square, kill chi. We can do so for beta, kill beta, kill gamma, and so forth. Every distribution. Okay, so that's for the quantile. Is everybody okay with this? Any question? So quantiles. So we are done with quantiles. What about density? So density will mean that, you see what we have over here. So this is the probability density, right? And these are the quantiles. So if I want the densities, then I must have my x values, and then I put it within the function, then I get the probability. Is everybody okay with this? Please, are you okay? Okay. So remember the quantiles, what we were inputting in is what? The probability. Then you get the value. Is that okay? Remember, in your normal tables, certain times we give you the quantile, then we say find the probability. That's where you do the inverse. And I think we ask this in 112. Sometimes we think it's 2. So we leave it for 201. 221. 221, yeah. So the inverse. So if I have some values, I can generate the densities. Is that okay? Is everybody okay with that? Okay, so let's see how that will be done. So densities. And this one, I'll ask you questions on it because soon, when we give you, let's say, the claims data, we will ask you to fit a distribution to it. When you finish, how do you check whether the distribution fits the data, or you have to superimpose the densities on the data? which means you need a histogram, and that histogram cannot be a frequency histogram. It has to be a relative frequency histogram. Then you superimpose the density on it. Okay. So let's just get some sample. Okay. So let's say, or let's say we call it data. And this data, let's take the package mass. Please, let's follow straight up. I think there's insurance. Yes. So that's in package mass. This one is what? Claims. It's okay. Let's. So insurance claims. Okay. So let's run this. We can get a histogram of this data quickly. Does it look like a normal distribution? No, right? But we can fit this data with a normal distribution and get the densities. Okay. Now, this, if we want to superimpose it on it, frequency should be false, right? So that we get something like that. So you see why we were doing, so the density will be like that. We cannot fit a distribution function on this. You cannot have a probability that is 40. As in counting, 1, 2, 3, 40. Remember, probability is a value between what? 0 and 1. So if we want to superimpose a density curve on a data, we can only do so if we get what? The density plot. Okay. So let's move on. Let me get this data done well. We don't need the main. So this, okay, and SLab I can give it. Please ask for plots. As I said, this is the last computing subject for you. So I cannot give you a data to plot and then you give me anything. It must be neatly done. So this one is claims or claim amount. It's not amount, I think number of claims. So let's just say claims. So there it is, nicely done. Okay. All right, okay. So now we are going to get the density. So we calculate the densities. So I call it dense. So I can go back to help. If we want densities, what are we going to, density of the normal distribution? It should be D norm, right? This is not good, but let's I'm just trying to fit what? A normal, standard normal distribution, superimpose it on it. That shouldn't be the case. If we want to fit this, we need to go through the 333 route, use maximum likelihood of method of moment to fit the data to a normal distribution in order, but that's not the case of just calculating the mean and the standard deviation. Okay, if it's maximum likelihood, we need to actually get a likelihood function and do what? Maximize it with respect to what? The data that we have. Okay, but this one is just practice, so let's see. So all we have to do is to provide the data here, right? Is that okay? So this one should give us the densities. So let's see how this density looks like. So let me just get a histogram of it. So that's it. But look at the way it is. The density is down. It's giving you just how many are between what? 0 and 0.1 and so forth. Okay. So we are going to fit the same density on the previous one, right? Which is this, the claims data. So how do we do that? We need lines, right? Because we already have the plot. So if you have plot and you want to put, if it is point, okay, if you want to get, then it should be point. If lines, you use lines. But that's secondary, so you must have a plot before you can use lines or points and so forth. So what can I do? Let me use points and then lines as well. So if it is points, will this work? Maybe. Then I need data as my x, sorry. X is equal to what's happening? X is equal to data, y will be density, right? So y will be what? The density we have computed. So let's see. So this is how it looks like. Okay. If I use lines, so you see it's not really capturing this well, and that's supposed to be, because normal distribution, if the data is, if you let's say a box plot, you realize that this is highly skewed. Normal should have the same what do we call it? Right tail, left tail. It's symmetric, so you don't expect it to capture the tails of the distribution wall. Okay, so let's see. If it is lines, we can also do the same. Lines, and then we can put this there. We can color it, maybe 2. We can give it a line width bigger so that we see how it looks like. Okay. And I will explain why this is so. So by the time I finish this, I have solved the problem I wanted you to go home and solve. Okay. But this is what is happening. You see, when we did points and so forth, they were haphazardly put on the graph. The reason is simple. If I say lines, remember lines will be joining the first one with the second, the third, and so forth. So the data will not be arranged in either decreasing order or increasing order. It will be haphazard. So if this one is here, it will join this, that's why you are seeing that over there. So to be able to get that smooth curve that you want, you need to order them. And that's the example I said you should do. That's why I asked you the first question as to ordering. So what it means is that we need to take either x, the data itself, order it in either ascending order or descending order. Of course, it must go with what? Its probability. So that when we start with the first one, the second one will still be the next larger one or the next smaller one, and then it continues until we get to the end. Other than that, we won't get a smooth curve, and it will be something like this. So unfortunately, I have to solve my own problem. So, okay, so how do I do that? Well, please, if you have any question, you ask before we move on. Because I'm going to give you an assignment when I finish. Now that I'm going to solve my own problem. So ordering, please make sure you do this. What I'm going to do, or let me just see the video on ordering, sorting, and ranking on YouTube. Okay. So how do we do so? Let me get my data now. I can make it a data frame of data and the density. what was it? It was dense, right? So let's say density is equal to dense. Okay. So if I go here and I check data, data is like, so you see what I was talking about. The first number is 38. The next one is 35, 20. So it's haphazard. What we are going to do is that we are going to order them such that either the highest value comes first and then it decreases, or the smallest comes and then it decreases like that. Is everybody okay with this? Which means each observation in the data goes with its or corresponding probability. So in Excel, if you do this, you need to do what? Expand the selection. So that each row will go with what? All its data. Other than that, you distort the probabilities with this data as well. So how do we go about this? Well, let me name it as data. So I need to call the data, and then I bring the selection sign, right? So I need to order. What am I ordering? Well, it's the data, right? Is everybody okay with this? Within the data, the first column, or I can use the first column as well. So what it means is that I need to also bring the question, comma, so that it takes each row. So I mean, order the first row, but you must take along what? All the rows and so forth. So let's see how this will look like. So I've already solved my problem. So it's S data, right? Now let's compare S data and data. What do you see? So it has all. So order means increasing order. If you want decreasing order, you have to go to order and put decreasing is equal to true. And then it will turn it the other way. Please, is everybody okay? Now, so this is what I wanted you to do with that one. So now I'm in a position to now go to superimpose it. And now we'll get our smooth curve. Okay. So I hope you are following. Of course, we'll get a video to it. So I need to first get this histogram done again. Okay. So now I have a problem because I should have named it differently. So there it is. This is our histogram, right? Okay. So now, what I'm going to do is to use lines. So lines. Okay. You need X. So X will be data. No, S data, right? S dot data, data. And then Y will be what? S dot data density. Okay, do we want to color? Maybe yes. We want to color it. This is a line. So we want red. Let's red. We want the line width to be big. If we want the line width to be big, we can increase it. 1 is the default, and so forth. Even the line type. You can also have line type. 1 is solid line, 2 is and so forth. Okay. You can add on to it. Let me add one line type, maybe 2, which means we'll have some broken lines. Oh, sorry, I made a mistake. This should be comma. There we go. So it doesn't really fit this quite well. So, but we are no more getting what? Those haphazard, yeah. Just that the distribution doesn't fit it well at all. So what we need to do is that later on, the same data will go and estimate the parameters of the normal and fit it to realize that that one will fit it better than what? The standard normal. And we'll do this as we go on with this. Okay. So what have we done now? We've seen how probability distributions are stored in R. how you can compute densities, how you can compute quantiles. We can't do everything. It means that you can also compute what? The P, which is the density. Remember, the cumulative distribution, you need X, right, to do it, to get your values and so forth. All right. Now, let me talk about random numbers. So random variates. Before we come to this one, I haven't forgotten. So random variates, which means generating random observations from a distribution. So in this case, we'll use R norm. So let's say X is R norm. So how many do you want to generate? Maybe 100 observations. The mean is 0. Standard deviation is 1. So let's do this. We generate. Let's do a histogram of it to see whether this actually represents a normal distribution. Ooh. What happened? So X main is equal to null. Okay, so you see this one somehow mimics a standard normal. We can increase it. I can increase the sample size, and we'll even be getting a better graph and so forth. Okay. So you see the way normal distribution is. If we now generate the density and we superimpose it, you realize that this one will be better because it's coming from the same distribution. Unlike the one that was like that. Okay, this is like this, so we can do that. Okay. Any question? Okay. What do I mean? I can line this X and density, not density, D norm X. Color is equal to red. So this will give me that haphazard. Oh, sorry. I should have done. Okay, so this is very important. Please look over here. This is in exam and the examination condition. These are some of the things I always get from students. Why do I have the line over here? The graph is frequency. So you will be there. I have my histogram. Why is it that because this line is between 0 and 1. Is that okay? So it means I need to go back. The histogram I plotted, the days should be false. So that it now becomes this, and then I can line this. So this is what I was talking about. So that haphazard drawing, but you still get the shape. And this one follows a normal distribution better than the one we were doing. And this, I can get a smooth curve that goes round it like that. If I now combine it, order, and do that. So I'm going to do that. Oh, I wanted to do this, and I'm wasting my time. Can you do that at home? This one. So what do I have to do? I need to come here. No, let me continue. To obtain a smooth line, a smooth density curve, what do you need to do? You need to order. So let me say this is SN data will be X. No, I need to combine them before, right? You see, when you are in a hurry. Okay, so data.frame. It's the same thing, so please don't say I'm in a hurry. X, and then density is equal to D norm X. Okay, so there we go. So this SN data, oh, no, let me do it N data. Then this one will be SN data. So it means I have to take N data. This is X, right? So N data X. Okay, and then of course we'll have N data here, right? So let's see. Okay, so now I can now bring my lines again. I'll take X, small x as SN data X, and then my Y as SN data density, and the color is true. But I need to go and do the graph again, right? So haste, and then now we're going to get a smooth curve. Oh, sorry, a smooth curve over there. Please, are you following? So this is the sort of thing we will be doing later on. So maybe we have a claims data. We think log normal is the best distribution. We'll go through 333 concept to either use a maximum likelihood, method of movement, least squares to find the parameters, estimate of the parameters. But how do we check whether log normal is better than Pareto or a gamma distribution or what have you? We need to be doing some of these. That's why we've taken our time to go through plots and so forth. Please, if you have issues with this, go to the YouTube page. Make sure you're able to go through all the plots because you need them to do all what we are doing now. So this one, even though we generated the observation from a normal, standard normal, you see it's still not capturing the top part, right? Yeah, and so forth. And that's what randomness is about. Okay, lastly, before I take leave of you, so tomorrow you have to come, okay, to class. Okay, now let's, okay, I have just 4 minutes. Let me hurry up. Okay, now remember that we can also generate observation from a exponential distribution by using RS. So let's say that E data, let's quickly generate this, is RSP. So N is equal to, let's say, 100. The rate is the lambda. So let's take lambda is 0.2, which means our mean will be what? 2. Is that okay? Because the mean is the inverse of what? The lambda. Is everybody okay with it? Good. So let's do that. Let's get a histogram of this data. Does this look like an exponential distribution? Does it look like an exponential distribution? Aja? Yes or no? Or you can't see? Hey. Okay. Does this look like an exponential? Yes. Okay. So if you look at it, it looks like we can even generate more, and it even looks even what? Better. You see an exponential decay. And just a moment. Hello, Eric. Hello. Yes. Sorry, I'm teaching. Okay. Okay, and you'll be tomorrow, yeah. Okay, then do it like that. Okay. Now, Nancy, also on yes, can you? How much am I moving? Okay, me what department and he said, obey na manabeja. And yes, obey my train, just about 20 minutes I should be there. Yeah, 2 minutes I will be there. Okay. Okay, all right, thank you. Okay, sorry. So give me like 5 minutes. Okay, please, is everybody okay with this? Okay, so now what we want to do is that we should be in a position to superimpose the exponential distribution on this. Is that okay? I'll leave that part to you when you go through the same concept with it. Is that okay? Good. What I want us to do now is to be able to generate the observations here. Is it the Chinese people are coming? Okay, so 2 minutes. Okay. Now let's do the same exercise. Let's write a function, quantum function like this. What do we do now? We need a function that takes lambda, right? And it will take what? Some p. But that p, we can generate it from exponential. Sorry, uniform. Good. Okay, so let's write a function very quickly. So my ESP, how do we write a function? Did I? It's okay, let's go tomorrow. But we did functions in 240. I thought I have. So it's okay. So please go. We have some recordings on functions. Please make sure by the time you come tomorrow, you have written the function to do this. So the function takes argument lambda and what? P. But the P can be sample size because you can now use R unit for the uniform distribution to generate from that, and then you put it in and you get your exponential. So please do so, and then also superimpose an exponential curve on this. We will do a class exercise tomorrow. Yes. Yeah. Okay, I'll check. So this one we can do so.